so next talk is going to be on advanced features of OpenMM. So this is sort of a schematic diagram of the architecture of OpenMM. I told you in my talk yesterday that OpenMM really is several different things and can be used in different ways by different types of users. And if you can see this a bit reflected in the architecture, at the very top level is the Python-based application layer, which is what pretty much all the talks so far have focused on. The next level below that is what we call the public API. This is natively it's a C++ API, though we also have wrappers for it in many different languages, including Python, C, and Fortran. And this is the language or the interface that you use if you're writing your own application and want to make use of OpenMM to perform calculations. But also this API is exposed through Python and is actually, in a sense, forms part of the application layer API. So what I want to do now is actually move our discussion down one level and start talking about the OpenMM public API. Now, if you're just going to be running simulations with OpenMM, you don't necessarily need to know any of this. But some of you may want to use OpenMM in other ways. And in addition, even if you're just running simulations, it's very useful to know something about this because it's a very, very powerful interface, and it lets you do a lot of things that would be completely impossible in pretty much any other MD code. And so even if you're just going to be running simulations, I want to just tell you a bit about how the OpenMM public API works so that if you want to and if you see the value in it, you have the ability to use those features. So what I'm going to do now is describe to you the whole OpenMM public API, and I'm going to do it in a total of 3 slides. So it's going to go really quickly, but you'll see it's actually a really simple interface. So there's just a small number of classes you need to know about. The first one is called System, and you've already seen the System class because it's come up in your example scripts. But just conceptually, what a system represents is a collection of interacting particles. That's really what we mean when we talk about a system in OpenMM. And the system class defines a small set of information that's related to this. So it defines how many of these particles there are. It defines what the mass of each particle is. It can define things like distance constraints between those particles and similar things like virtual sites that come up in certain force fields. And finally, it defines a list of force objects that describe what the interactions between these are. And I'll get to the force objects in just a moment on another slide. The next class, which is one you again have already seen, is the context class. The context describes all the information, all the state information about a simulation that's in progress. So what are the current positions of all the particles? What are the velocities of all the particles? And it can potentially describe other parameters, like if you're running a constant pressure simulation, so your box size is changing, then your box size will be contained in the context. In the examples you've done so far, you actually created a slightly different class that's related to this, which is the simulation class. But then you would have lines in the code where it would say simulation.context. So really, a simulation is an application layer class that's just a thin wrapper around a context. When you create the simulation, it automatically creates the context for you. And simulation adds a few other features on top of it, like the ability to attach reporters. OK, so force. So the system does not directly define what the interactions are between the particles. It does that by defining a list of force objects. And a force is basically anything that affects the system's behavior. So the name force is actually a little misleading, but we were never able to come up with a better name. Many force objects are, in fact, forces, like, the force created by harmonic bonds or your Coulomb interactions between particles. But also things like thermostats and barostats can also be forces in this slightly expanded sense of the word. It's just anything that affects the behavior of the system. So to be more explicit about what a force object is or does, it may apply forces to the particles, obviously. It can add a contribution to the potential energy, because The forces are supposed to be the gradient of the energy, so if you apply forces, that means you are also affecting the potential energy. A force object can define adjustable parameters. So for example, in one of the examples yesterday, you saw Monte Carlo barostat, which is a barostat, but it is implemented as a force object. You added it by calling add force on your system. And the barostat defines some adjustable parameters, like what is the pressure, and you can change that pressure in the middle of a running simulation. And finally, a force object has the ability to modify positions, velocities, and parameters at the start of each time step. For an example of this is the Anderson thermostat class, which is a force object, but it doesn't work by applying forces. Instead, what it does is at the beginning of each time step, it randomly selects a subset of particles in your system and modifies the velocities of those particles. And so this is another way that a force object can affect the behavior of your system. All right, last slide of the API. Just two more to talk about. One of them is integrator, and you've seen several examples of this already, like Langevin integrator and Verlet integrator. So an integrator is just something that advances the system through time. Different types of integrators define different methods of doing this. We have both fixed and variable step size integrators, and in fact, we even have something I'll mention later called custom integrators that can, actually I'm not sure if I'm going to mention them, maybe this is the only time I'll mention them here, but that you can define completely new integration algorithms. Finally, we have a class called state, which is basically a snapshot of the system at any moment in time. The way you create a state is to call getState on your context. And this creates, so a state object is immutable, whereas your context is constantly changing. It describes the current parameters of your simulation. If you want to query that, you call getState, and that returns to you this immutable snapshot of what were the values of those parameters at any moment in time. When you create that state, when you call getState, you tell it exactly what information you want to have in that state object. So it can include positions, it can include velocities, it can include energies, it can include forces, it can include parameters, but you tell it exactly what information you want, and only that information will be included. And there are important reasons that we chose to implement it this way, because when especially when you're working on a GPU, but also in other situations where you're like working on a cluster, retrieving this information could be very expensive. For example, if you're running on a GPU, the information about positions and velocities is stored in the GPU's device memory, and in order to get access to this, we need to transfer that information from the GPU's device memory into your computer's main host memory. And that's a somewhat expensive thing to do. It takes time. And so we don't want to do this. We don't want to retrieve any information except what you're actually going to want. And then when you do this, we want to retrieve it all in bulk because we can do it more efficiently that way. All right, so let's go through an example of how this might work in practice. So you want to create a system. All right, system equals system. Great, we just created a system, no problem. Now you want to add some particles to your system. So you loop over each of your particles and you call system.addParticle. So we are calling the addParticle method of the system. And we pass one argument to it, which is the mass of the particle that you want to add. So you loop over all of them, and great. You have now added all of the particles to your system. Now maybe you want some constraints in your system. So for every, you loop over whatever constraints you want, and you call addConstraint for each one. And you pass in 3 arguments to it. The indices of the 2 atoms whose distance should be constrained, and what distance should they be kept at. And you do this, and now all of the constraints have been added to your system. Now in the examples that you've done yesterday, you didn't do this. Instead, you called create system on a force field or an Amber parm.top file object or something like that. But if you actually look at the implementation of like the force field class, this is precisely what it was doing. So in these normal cases, you won't do these things yourself. One of these other classes will do these for you. But if you want to, you have the ability to do this. Now, suppose you want to add some forces to your class. So, for example, you want harmonic bonds connecting the bonded atoms. So you create a harmonic bond force object, and we'll assign it to a variable called bond force. And for every bond in your system, you will call add bond on your bond force object, and you will pass to it the indices of the two bonded atoms, and the equilibrium length of the bond, and the force constant. And having done that, now you've added all the bonds to this harmonic bond force object, and the final thing we need to do is call add force and on our system and say, okay, here's a force object, add this into the system. And now when you run a simulation with this, those harmonic bonds are going to be applied. The forces from them will be applied to those atoms. And of course, in practice, you will probably have a number of different forces that you have: angle terms, torsional terms, non-bonded terms, etc. Okay, now you want to run a simulation. So you're going to create an integrator, and you've already seen that. You created an integrator in your earlier examples. And now you will create a context, giving it the system and integrator. This looks almost exactly like what you did before, where you created a simulation object, and that simulation then created the context object for you. We call set positions, set velocities to tell it what we want the initial positions and velocities to be. And then we call step on our integrator, just like you've seen before. And that runs the simulation. Now, the final thing you'll want to do is to retrieve back some state information. Again, in your examples before, you probably weren't doing this because you were using a reporter, and that reporter was taking care of all of this for you. But if you want to get state information, you just call get state on your context. And in this case, we're saying get positions equals true, get velocities equals true. So this state that is returned to us will include positions, and it will include velocities. It will not include other things like forces or energies because we didn't ask for them. But if we did want them, we could have asked for those. And now we might, for example, just loop over, we'll call state.getPositions. That returns to us a list of the positions of every atom, and we loop over them, and in this case, we're just printing them out, for example. But you could do whatever you wanted. All right, really important topic I want to talk about is platforms. And you've all seen some uses of this already. So again, like I said yesterday, the API defines the interface. It's how you specify what calculations you want to do. The platform provides the implementation, the code that actually performs those calculations. And OpenMM comes with 4 different platforms. There's the reference platform, which you never want to use in practice because it's very, very slow, but it doesn't make any attempt to be fast. The goal of the reference platform is to be very simple code, easy to write, easy to understand. We can then, when we're writing other platforms, we can use it as a starting point for exactly how the algorithm should be written, and we can compare our results to it to make sure that, when we're writing much more complicated GPU code, for example, to make sure that it's giving the right result. The CPU platform also runs on your CPU, but unlike reference, this is actually a fast platform. It's multi-threaded, vectorized code, etc., so it actually tries to be fast. And then we have OpenCL and CUDA platforms for running on GPUs. And OpenCL can also run on CPUs. So there is an API for working with platforms. It's very simple. And let me just show you a few of the things that you might want to do regarding platforms. So the first thing is that you may want to specify what platform to use for your simulation. If you don't specify a platform, OpenMM will just try to guess what it thinks will probably be the fastest platform for you. And usually it guesses correctly, but not always. And sometimes you want to specify it. And it's really easy to pick it. You just say, use the platform class to say platform, get platform by name. You give it the name of the platform you want. That returns a platform object. And then when you create your context, you just pass that platform as the last argument. And you can do exactly the same thing when you create a simulation object. You can just, after specifying the integrator or the system and the integrator, just pass the platform as the next argument, and it will then use that platform. Another thing you might want to do is maybe you're fine letting OpenMM pick the platform, but you just want to find out which one it picked. And so you can just call context.getPlatform.getName, and that will give you the name of the platform that is being used. useful thing to print out just as output from any simulation, just so you'll have a record of what it was using. One other thing you might want to do is just list what are all the available platforms, because that will vary depending on your computer. Like, if you have CUDA installed and you've got an NVIDIA GPU, then you'll have the option of using the CUDA platform. If not, then you won't have that option. And so it's good just to know what are the available platforms. And the way you can find this, you can call platform.getNumPlatforms to find out how many platforms are available. And then for each one, you can just call platform get platform I, the index of that platform, get name, and that will give you the name of the ith platform. Any questions on that? All right, so that is the basic OpenMM API, and it's pretty simple. But now I want to go on to some more advanced features to show you some of the really, really powerful things that you can do. So let's talk about forces. OpenMM comes with implementations of most of the standard forces that come up in molecular dynamics simulations. Harmonic bond force, harmonic angle force, non-bonded forces, your standard Coulomb and Lennard-Jones, etc. And for most simulations, this pretty much covers all the basics. But sometimes you want something else. What if you are running a simulation and you really want some other type of force that OpenMM hasn't provided to you? What do you do? All right, well, OpenMM is based on a plugin architecture, and you can write plugins that add new features, and certainly one option is that you could write a plugin, and that plugin would implement a new force. You probably don't want to have to do this. You absolutely can, and there are some situations where this is the right answer, but it's a lot of work, and especially if you're going to be running your simulation on a GPU, this involves writing GPU code, which is a pretty specialized thing to know how to do. It's difficult, it's a lot of work. So is there a better option or an easier option? And the answer is yes. OpenMM has this very remarkable feature called custom forces. And the goal of custom forces is to provide some of the flexibility of a plugin with most of the simplicity of using a standard force. And the idea is you just give us an equation, an algebraic expression that is what you want the energy of your interaction to be. And OpenMM will do all the rest for you. So you would simply, for example, here is custom non-bonded force, and then in quotes it has this little mathematical expression that's a function of r, the distance between two particles, and then you can just have this applied to all your particles as a non-bonded interaction, and every pair of particles in your system will interact with each other with this energy expression. In fact, we have many different types of custom forces, because each custom force is specific to a particular type of interaction. So, for example, we have custom bond force, which is a bonded interaction between two atoms, where the energy is a function of the distance between those two atoms. So just like harmonic bond force, except it doesn't have to be harmonic. It can be any functional form you want. Similarly, we have custom angle force, where the energy is a function of the angle formed by three particles. Custom torsion force, where it's an interaction between four particles, and it's a function of the dihedral angle formed by those four atoms. We have one called custom external force, which is sort of like an externally applied force or externally applied potential. So this is a force that's applied independently to every particle, and the energy can be a function of the position of that particle or also of other parameters that you can specify. Custom non-bonded force, which you already saw, that's a non-bonded interaction where the energy is a function of the distance between the pairs of particles. Custom compound bond force is a bonded interaction, but it's much more general. In fact, it can reproduce any of the bonded forces you've seen already. So a bond is considered to can involve any number of particles, not just like 2 as in bond force or 3 in angle. It can be as many as you want, and the energy can be an arbitrary function of any set of positions, distances, angles, and dihedrals. So this can be very powerful for many different types of more complex interactions. Moving on to some of the more complicated ones, we've got custom GB force, that's for implementing implicit solvent models. Primarily generalized Born, but it's actually more general than that. It can implement a variety of different sorts of implicit solvent models. We have one called custom H-bond force that can implement a wide range of different hydrogen bonding interactions. One important thing to know about is the performance of custom forces, and this varies widely depending on what platform you're using. So if you are using the OpenCL or CUDA platforms, what OpenMM actually does is take your expression, generate OpenCL or CUDA source code, generate a new kernel, send that kernel to the kernel compiler to generate your GPU's native machine code, and it does all this at runtime. So the result of this is that custom forces run just as fast as standard forces. There is little or no performance penalty to using one of these things rather than a corresponding standard force. And so when you're using the OpenCL or CUDA platforms, you can use custom forces for pretty much anything and not have to worry about any sort of performance cost in doing this. Now, the CPU and reference platforms, they aren't able to do that. They have to use a little interpreter to evaluate your expressions, so the custom forces will be much slower than standard forces. Whether that's a problem depends entirely on what you're doing. So like a custom bond force or a custom external force, usually this isn't an issue, even though it's slower than like a harmonic bond force would be. The bond forces are still so fast compared to the non-bonded forces. They usually just aren't the bottleneck, and so you don't have to worry about this. On the other hand, if you're doing something really complicated like a custom GB force, usually like with the CPU platform, that would be too slow to be useful. And you'd want to use those preferably on a GPU if you can, where there isn't this performance penalty. So let's show an example of what you might use this for. So this is an example where you want to simulate a droplet of water. So, instead of having like a periodic box of, of water that's supposed to represent an infinite bulk of water, here we want to simulate just a single droplet. Now, you can simulate a little droplet of water, but if you just simulated that like in vacuum, all your water will eventually evaporate away, and you won't have a droplet anymore. You'll just have lots of water molecules floating off to infinity, and that's not so useful. So what we want to do is put a wall around it, just so that when a water molecule tries to float away, it will get pushed back, and our droplet won't be able to evaporate. And so this example is almost exactly like the examples you've already seen, except for the addition of these 4 lines added here. So what we say is force equals custom external force, and then we give it this expression for what we want to the energy of this interaction to be. One thing to notice here is that we can actually define sub-expressions, variables within the middle of it. So right here we're defining, and you do this just by putting a semicolon after your expression and then giving the definition. So we're saying r is the square root of x squared, y squared, z squared. So we're just defining r to be the radius of the particle, its distance from the origin. And then we give this little expression here for what we want the energy to be. So what this is basically a harmonic potential, but it's flat initially. So out to a radius of 1 nanometer, units are always in nanometers here, so it's going to be 0 because we're taking r minus 1 and then max of that in 0. So it'll be flat out to a radius of 1 nanometer, and then beyond that it will just go up harmonically. And then we go through and we loop over every particle in our system, and we call add particle on the force. So custom external force, it can be applied to as many or as few particles as you want to, and it just depends on your application. In some cases like this, we want to apply it to every single particle, and so we'll call add force for every particle. In other cases, you might want to apply it to only one particle or only a few particles. And so you call add particle, and you pass in the index of the particle to apply it to, and then that second argument, which in this case is just an empty tuple, is the parameters to use, the per particle parameters, since you can define parameters that are specified per particle. In this case, we don't have any, so it's just an empty tuple. And finally, we call add force on the system to add it in. So what I want you to do now is try this out. So you have this example in your tutorials directory, and the first thing I want you to do is to just run the water sphere example, and it will write out a PDB file called output.pdb, and then view those results in VMD and see what it looks like. And once you've done that, I've got a couple of other exercises for you to try, and so go ahead. You all managed to run the example and view the results in VMD, and can anyone say what it looked like? Right. So yeah, if you notice in this example, we specified a temperature of 1,000 Kelvin. And the reason that I did that is that if I didn't make it very, very hot, then you wouldn't see it. You never even notice that that sphere was there, except in the rare occurrence when one molecule tries to evaporate and float away. Which is probably what you do in a real simulation, but it makes a bad example here because you can't even see the fact that the sphere is there. So I just push the temperature way, way up, and then it fills the sphere with a cloud of like really hot steam. But when you reduce the temperature to 300 Kelvin, well, at 300 Kelvin, water is liquid, and so it condenses into a droplet. And how about the increasing the sphere radius to 2 nanometers? Who figured out how to do that? Yeah, and how did you do it? What did you change to make it be 2 nanometers instead of 1? Right. So basically, you're just changing the shape of that potential function. And some people asked about that 10 in front. That's just setting the magnitude of the force. So we're just saying how strong is this force going to be. One other thing I wanted to mention were several questions about units in this. So the units can work 2 different ways in OpenMM. In all the Python examples you've seen, you are actually explicitly specifying units on things. Like in this example here where we said like 1,000 times Kelvin, 0.002 times picoseconds. And that's a feature of the application layer. It knows how to deal with quantities that have units on them. So you can explicitly tell it units, and then you can use whatever units you want. So for example, you can measure your distances in nanometers or angstroms, whichever you prefer. And as long as you specify that, it will get everything right. But that's at the Python level. The lower level C++ layer does not know about units, so it works a different way. It just has one standard set that it uses for everything. And it expects that all quantities that it sees will be in those units. And in fact, the interface between the Python layer and the C++ layer, that's where the translation layer is, the translation between those is done. And if you look in the manual, you can find a description of what those standard units are. But basically, distance is always measured in nanometers, time is always measured in picoseconds, energy is always measured in kilojoules per mole. That's a very important one to be aware of. Some applications use kilocalories per mole, which is actually a really bad choice because it leads to an inconsistent set of units, so that like a force doesn't always have the same units depending on how you calculate it. But OpenMM has a standard set of units, and they do form a consistent set. So there's just one other thing I wanted to talk about is just how to get help on this, where to go for more information. The first thing, of course, is the manual. You've all looked at the manual. It has lots of detailed documentation on all of these things, and so that's a very good place to go for information on anything. Another thing is just this diagram here. It's a lot of arrows and things pointing all over the place, but it does present a lot of information really compactly. You can get this diagram if you just go to the OpenMM website and you click on the Documents link of the sidebar, and this diagram is there that you can download it. And it just shows all these things that, for example, we can see that, see here, for example, is the system class. And we see that, a system contains forces. It is required to create a simulation. A system can be created by any classes here, like Amber Parm top file, Gromax top file, Desmond DMS file, etc. And this just shows the relations between all these different classes. And so just for a very high-level overview of how all these different important classes are organized, this is a good thing. The other important place is the API reference documentation. And if you, when you installed OpenMM, if you look in your docs directory, you will find that you've got this there. And there's actually two different versions of it. There's one for the C++ API, and there's one for the Python API. And you can double-click on either of those, and it just gives you a nice index, every class, and then detailed information, description of how the class is used, every function that you can call on it, lots of information on how to use all of those. And so that's just another place that you can go for documentation. And finally, as we discussed earlier, we do have a discussion forum, and if you have questions, absolutely go to that forum, and we're happy to answer questions there.